In our last module, we talked about the cycle notation. And in this module, we're talking about a fairly closely related topic, namely cyclic subgroups and the order of an element of a group. First, I just want to review what we know about exponents and maybe add a little bit more, exponents in a group, that is. So suppose we have a group and an element A of the group, and n is a positive integer. We know what a to the n means in the group. It means that you use the group operation to combine n factors of a. It's fairly easy to extend this to negative exponents for elements of a group. We define a to the minus n. If n is a positive integer, a to the minus n is defined to be what you get when you combine n factors of a inverse using the group operation. And then finally, we could also include n equals 0 as a possible exponent by defining a to the 0 to be the identity element of the group. So we'll be doing some examples very shortly, but first here's a useful tool for calculating a to the n in the specific groups of the type u sub m and times sub m. This is something a lot of you discovered in our last writing project. So if you take a positive integer n, in the group u sub m times sub m, a to the n is the same as a to the n calculated in the integers. This inside the parentheses here is an ordinary exponent. And then you take the answer mod m. So for example, if we look at the group u sub 7, and we want to calculate 3 to the 5th in this group, we could do this by simply calculating 3 to the 5th using ordinary exponentiation and then taking the answer mod 7. Right, 3 to the 5th is 243, mod 7 is 5. So let's try a few exponent examples. We'll stick with the group u sub 7 times sub 7. What is 3 to the 4th in this group? This means that we are multiplying 4 factors of 3 using times sub 7. One way to do it is to group the multiplication like this, with the first 2 3's grouped together first, followed by the second 2 3's. And if you did that, then you would calculate 3 times sub 7 3, which is 3 times 3 mod 7. That would be a 2. And then you would multiply 2 times sub 7 2 to get 4. So this is one possibility for calculating 3 to the 4th in u sub 7. Another possibility would simply be to calculate 3 to the 4th using ordinary exponentiation and then take the answer mod 7. 3 to the 4th is 81. 81 mod 7, see the remainder when you divide 81 by 7, is 4. Let's try 3 to the minus 4. Still calculating in u sub 7. According to our definition for negative exponents, we combine 4 factors of the inverse of 3. So we're going to need the inverse of 3 in u sub 7. which I found by trial and error. The inverse of 3 is 5, because in U sub 7, 3 times 5 is 1. 3 times 5 is the identity element. So 3 to the minus 4, a little typo here, this should be 3 to the minus 4, would be 3 inverse times sub 7, 3 inverse times sub 7, 3 inverse times sub 7, 3 inverse. I got an extra times sub 7 here I have to get rid of, which we could do this way. Since 3 inverse is 5, we could do 5 times sub 7, 5 times sub 7, 5 times sub 7, 5. 5 times 5 in U7 is 4, and 4 times 4 in U7 is 2. Took a brief minute there to correct the typos. And then finally, let's calculate 3 to the 0. 3 to the 0 calculated in a group is the identity element from the group, so 3 to the 0 is 1. And now, with these definitions of integer exponents, the following laws are fairly easy to verify. If you combine two powers of a group element A using the group operation, a to the m star a to the k, which we would ordinarily write as a to the m a to the k, following the convention of leaving out the symbol for the group operation, that can be calculated by doing a to the m plus k. This is a rule for exponents when we're doing ordinary exponentiation with real numbers that you know. And similarly, a to the m raised to the k power can be calculated as a raised to the m times k. This rule that holds when you're working with exponents in a group is the same rule that you know about for ordinary exponents. And it's not hard to see why these rules are true by looking at a few examples. Let's try this. What is 3 to the third to the second? Well, raising something to the second power in a group means you combine that thing with itself using the group operation. A to the third to the second means, by definition, a to the third star a to the third. And a to the third is shorthand for a star a star a. So now we simply count up the number of a's that we're combining using the operation star. We have 2 blocks of 3, and 2 blocks of 3 is what you get when you multiply 2 by 3, a to the sixth. So the actual proofs for these rules, if we were going to do the proofs, for positive n would be by mathematical induction, and then the rules when the exponents were not necessarily positive, we could prove using the rules for the fact that the rules are true for positive exponents. Okay, so why don't we try another example. We'll work in the group S sub 5. So this is the set of all permutations of the numbers of the integers 1 through 5. As usual, we're using the operation of function composition. Here's a sample element of that group given in cycle notation, so it's a cycle of length 5. So we simply want to calculate alpha to the fourth and alpha to the minus 2. And we want to write the answer either as a single cycle or as a product of disjoint cycles, which we know we can do. Right? Every permutation of a finite set is either a cycle or a product, or can be written as a product of disjoint cycles. Okay, so let's try alpha to the fourth. Now here's how I'm going to do this. I'm going to start a cycle with 1, as we usually do when we're multiplying or working with cycles. And now I want to decide which number between 1 and 5 1 is taken to by alpha to the fourth. So I go back up here to the cycle that defines alpha, and I apply it 4 times. 1 goes to 3 is one application, 3 goes to 2 is the second application, 2 goes to 5 is the third, and 5 goes to 4. So applying alpha 4 times in succession to the number 1 gives us a 4. And similarly, we could now apply alpha 4 times in succession to the number 4. 4 goes to 1, that's once. 1 to 3 is the second application. 3 to 2 is the third. And 2 to 5 is the fourth application of alpha to the number 4. The net effect is that 4 goes to 5. And similarly, 5 goes to 2, and 2 goes to 3, and 3 goes to 1. So that closes the cycle. So there's alpha to the fourth, calculated in more or less a single step. We also know that the inverse of a cycle of length 5, cycle alpha of length 5, is alpha to the fourth. This is something we learned in our previous video on the cycle notation. And we also have a way of getting the inverse of a cycle alpha. You list the elements in reverse order. Alpha inverse is 4, 5, 2, 3, 1. And since alpha to the fourth is the inverse, we know that alpha to the fourth is 4, 5, 2, 3, 1. So this would be a second way of calculating alpha to the fourth. And one thing to notice is that these two answers, 1, 4, 5, 2, 3, and 4, 5, 2, 3, 1, are two ways of writing the same permutation in cycle notation. Right here we've written it as a cycle beginning with 1, and in our second version we've written it as a cycle beginning with 4. But they represent the same permutation. And now alpha to the minus 2. So here we would need to find alpha inverse. Well, actually, we know how to find alpha inverse. You simply write the numbers in the cycle in reverse order. The inverse of a cycle of length 5 will be a cycle of length 5. So the inverse of the cycle 1, 2, 5, 4 is 4, 5, 2, 3, 1. And then multiplying these two cycles, guess I did the whole thing at once here. So we would be, remember when you're multiplying cycles, you work from right to left. So we would first plug 1 into the rightmost cycle. That sends 1 to 4. And then we would plug 4 into the cycle on the left. The cycle on the left sends 4 to 5. So the net effect is that 1 is sent to 5. And similarly for the last 3 elements of the answer. One thing to keep in mind is that if you have the identity in a group, then for every integer n, e to the n will be will be E, right? No matter how many factors of E you combine using the group operation, you will always get the neutral element or the identity back again. And another thing to note is if you have an element of a group and you take any two integers m and k, then a to the m times a to the k, as we know, is a to the m plus k. And now here in the exponent we are adding two integers, and we know that integer addition is commutative. So a to the m plus k is equal to a to the k plus m, which, using our rules for exponents, is a to the k times a to the m. The point of this string of equalities is that powers of a commute. Any two powers of a commute. A to the m times a to the k will always be a to the k times a to the m. Not too surprising a fact. And then one other thing that we will have to be aware of, if we're looking at a group where the operation is some kind of addition. For example, the group z sub 7 plus sub 7. So what is 3 to the 5th, using our definition of exponents in a group, mean in this group? Well, it means 3 star 3 star 3 star 3 star 3 star 3, combining 5 factors of 3 using the group operation. But here the group operation is plus sub 7. Which is 5 times 3 mod 7. We're adding 5 3's here. And then taking the answer mod 7, which happens to be a 1. So for this reason, in groups where the operation is some kind of addition, if n is an integer, positive integer, then combining n factors of a using the group operation is often abbreviated n times a rather than a to the n. So now we're going to look at a special kind of subgroup of a group called a cyclic subgroup. So if you have a group, G star, this can be any group, and if you take any element, little a of G, then the set of all integer powers of A is a subgroup of G. And this is called the cyclic subgroup of G generated by A. And the shorthand notation uses these angle brackets. The cyclic subgroup of G generated by A is a left angle bracket A, right angle bracket. So in more symbolic form, we could write the cyclic subgroup generated by A using the set notation as a to the k, where k ranges through the integers. So this is another way of saying that the cyclic subgroup generated by A is the set of all integer powers of A. And then using sort of a listing method for describing sets, you could list the integer powers of A. So I put a to the 0 sitting in the middle here. That's the identity. A to the first will just be A. And then to the right, we list all the positive powers of A. And to the left, we list the negative integer powers of A. So there are a couple of ways of thinking of the subgroup generated by little a. And now we probably should consider the question, why is this a subgroup? Well, first of all, it's non-empty. At the very least, it contains a to the 0, which is the identity or neutral element of the bigger group G. It is a subset of G. This is because G is closed under the operation star and under taking inverses. So if you do that any number of times with an element A to get an element of the cyclic subgroup generated by A, you end up with something that's still in G. As we've seen, using our rules for exponents, if you take the product of two powers of A using the group operation, a to the m star a to the n, that will be a to the m times n, which is also an integer power of A. So this thing we've called the cyclic subgroup generated by A is closed under the operation star. And finally, so A is closed under star, right? And finally, the inverse of an integer power, a to the n of A, is a to the minus n, which will also be an integer power of A. So this thing that we've called the cyclic subgroup generated by A is also closed under taking inverses. And therefore, this thing we've called the cyclic subgroup generated by A meets the four criteria for being a subgroup. Here is one fact to keep in mind about this cyclic subgroup generated by little a. We argued earlier that powers of A commute, right? A to the k times A to the n will always be A to the n times A to the k, no matter what integers k and n you use. And therefore, if you take any group G, whether or not G is commutative, and any element A of G, the cyclic subgroup generated by A will be commutative. And now here's a pretty useful fact for finding, actually listing the elements of the cyclic subgroup generated by A in some special cases. So if you have a finite group G, so we're starting out with a finite group like U sub 7, and if you compute A to the 0, which is the identity, and then the positive powers of A until you reach the identity again, so you would be doing something like this. A to the 0 is the identity. A to the first would be A, and then A squared, and then A cubed, and you keep calculating positive powers of A in order until you finally reach the identity. We've called the exponent where that happens n in this case. So suppose you do this calculation, you finally reach the identity. Then the cyclic subgroup generated by A will be A to the 0, A to the first, A squared, and so on through A to the n minus 1. So what we're really saying here is that under the conditions described up here, that is where A to the n is the identity, every integer power, every element of the cyclic subgroup generated by A is one of the elements A to the 0, A to the first, A squared, and so on through a to the n minus 1. This is what we are claiming in this line right here. Every integer power of a will be one of these. And here's the argument. So remember, we're assuming that a raised to the power n is the identity. So take any integer power of a. We're calling it a to the k here. And then you divide k by n using the division algorithm to get a quotient which we'll call q and a remainder r. And the remainder is always greater than or equal to 0 and less than the thing you're dividing by, which is n in this case. So writing the division in equation form, k is q times n plus r. This is a familiar equation. And now we're going to take this integer power of a to the k, that is, that we started with, and write it as a to the q times n plus r, using the results of the division of k by n. And then we'll use the rules for exponents to simplify. So we'll have a to the k is a to the q times n plus r. This, according to the rules for exponents, is a to the q times n times a to the r. A to the q times n is a to the n raised to the q. And then we have the a to the r, which we haven't changed. A to the n is the identity. So we have, as our next step in this sequence of equations, the identity to the q is a to the r, and the identity to any power, as we saw earlier, is the identity. So this is e times a to the r, which is a to the r. So we've shown that a to the k is a to the r for some r between 0 and n. And that's exactly what we were trying to show. So let's try a couple of examples using this principle for finding cyclic groups. Let's find the cyclic subgroup generated by 2 in u sub 7 times sub 7. So we're going to calculate the positive powers of 2, working in u sub 7. So we have 2 to the first, which is 2. We have 2 squared, which is 4. We have 2 cubed, which would be 2 times 4, using, we're actually times sub 7 4, which would be a 1. And we've reached the identity by taking 2 to the third. This means that the cyclic subgroup generated by 2 consists of the elements 1, the identity, 2, which is 2 to the first, and 4, which is 2 to the second. And now let's find the cyclic subgroup generated by 2 in z sub 8 using plus sub 8. So we have to keep in mind here that the operation is plus sub 8. It's an addition, it's not a multiplication. So that's why I put the word powers in quotes here. We're calculating positive powers of 2, but these are really multiples of 2 when you are working with an operation of addition. So we're keeping in mind that 2 to the n in z sub 8 really means combining n factors of 2 using the operation plus sub 8. So 2 to the first is 2. Should mention that 2 to the 0 is the identity, namely 0. 2 to the first is 2. 2 squared is 4. That's 2 plus 2, using plus sub 8. 2 to the third will be 2 plus sub 8, 2 plus sub 2, plus sub 8, 2. That's a 6. 2 to the fourth will be, let's see, combining 4 factors of 2 using plus sub 8 gives us a 0 in z sub 8. So it's the 4th power of 2 that gives us the identity. That means that the cyclic subgroup generated by 2 consists of the identity and 2, which is 2 to the first, and 4, which is 2 to the second, and 6, which is 2 to the third. And now we are going to talk about the order of a group element. So we take an element in a group. We're calling it little a, and we're calling the group G star. And we're assuming the identity of the group is E. And now what is the order of the element A in the group G? Well, if there is a non-zero integer j for which a to the j is equal to the identity, then the order of A is the least positive integer, n sub 0, for which a to the n sub 0 is the identity. So if you can get the identity by taking non-zero powers of A, the order of A is the smallest positive integer for which that happens. If there is no non-zero integer j for which a to the j is the identity, if you never get the identity by taking non-zero powers of j, we say that A has infinite order. So why don't we try an example? We'll go to the group U5 times sub 5 and use the element A equals 3. So we're going to calculate positive powers of 3 until we get the identity. 3 to the first is 3 in this group. 3 to the second is 3 times sub 5, 3, which is 4. 3 to the third, 3 times sub 5, 3 times sub 5, 3 is 2. Three to the fourth we could do by multiplying 2 times sub 5, 3. 3 to the fourth is 1. 4 is the smallest positive integer power of 3, which gives you the identity. The order of 3, therefore, in the group U sub 5 times sub 5, the order of 3 is 4. Why don't we look at the group consisting of the positive real numbers using ordinary multiplication? Okay, so let's calculate positive powers of 3 in this group. This is ordinary multiplication. 3 to the first is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81, and so on. We will never get the identity by taking a positive power of 3. 3 has infinite order in this group. Let's try calculating the order of a cycle in a permutation group. So here's a cycle of length 6. We're in the group S sub 8. Well, we know that a cycle of length 6 raised to the 6th power is the identity. Alpha is a cycle of length 6, so alpha to the 6th is the identity. Is 6 the smallest positive integer for which this happens? Yes, it is. We can see that no smaller positive power of alpha is the identity by simply looking at alpha squared applied to 2. See, alpha squared applied to 2 is 4. Alpha squared is not the identity because the identity applied to 2 is 2. We'll look at alpha cubed of 2. Alpha cubed of 2, let's see, one application of alpha sends 2 to 5. The second application sends 5 to 4. The third application sends 4 to 7. Alpha cubed of 2 is 7. Alpha to the 4th of 2 is 3, which you can check. Alpha to the 5th of 2 is 8. So none of the smaller integer powers of alpha give you the identity. 6 is the smallest, so the order of alpha in the group S sub 8 is 6. And in general, the order of a cycle of length k is k. Not too surprising fact. And now a fourth example. Here we have an element of S sub 5, which is the product of 2 disjoint cycles. So what is the order of beta in the group S sub 5? Well, beta is a product of disjoint cycles, as I said, and we know that disjoint cycles commute. So if you calculate beta squared, for example, it would be a beta times beta, which I've written here, 2 copies of beta. The cycles commute. This could be rewritten as the cycle 243 times the cycle 243 times the cycle 15 times the cycle 15, which in abbreviated form would be 243 squared times 15 squared. And in general, beta to the n can be written as 243 to the n times 15 to the n. This is a consequence of the fact that disjoint cycles commute. So if we're looking for an n for which beta to the n is the identity, we are going to need for both 243 to the n to be the identity and 15 to the n to be the identity. I have both of these factors of beta in this displayed equation will have to be the identity if beta to the n is going to be the identity. In order for 243 to the n to be the identity, n is going to have to be a multiple of 3. In order for 15 to the n to be the identity, n is going to have to be a multiple of 2. So the order of the product, the order of beta, will be the smallest positive integer, which is both a multiple of 3 and a multiple of 2. In other words, the order is the least common multiple of 3 and 2, which is 6. And in general, if beta is a permutation, and you've written it as a product of disjoint cycles, as in our example, then the order of beta is the least common multiple of the lengths of the cycles. Okay, so why don't we try this example. So here is a permutation gamma written as a product of disjoint cycles. So what is the order of gamma? This first cycle has length 4. The second cycle has length 6. So the order of gamma will be the smallest number, smallest positive integer that's both a multiple of 4 and a multiple of 6. The least common multiple of 4 and 6. What is the smallest common multiple of 4 and 6? It's 12. Gamma has order 12. So one thing this example shows, thinking of it as sort of being a counterexample, the order of the product of two group elements is not necessarily the product of the order. Right, here is a cycle of length 4, here is a cycle of length 6. If you multiply the orders, you get 24. But the order of the product is not 24, it's 12. And now our primary tool for calculating powers of a to the k for large k's. We're talking about an element that has a finite order n sub 0. So suppose A is a group element and has order n sub 0. So that means that A to the n sub 0 is the identity in the group G star. There's a way of finding A to the k for any integer k. And I've phrased it as a lemma here. If A is an element of a group and A has finite order n sub 0, then for any integer k, A to the k is A raised to the power k mod n sub 0. This you may have discovered in the writing assignment for the last module. This is actually something we proved earlier in these slides. So let's try an example. We know that 3 has order 4 in the group U sub 5 times sub 5. We did this in an example earlier in this set of slides. So let's pick some large exponent. Well, 18 isn't too large. Let's calculate 3 to the 18th. Well, we simply find 18 mod 4. 18 mod 4 is 2. So, according to the lemma, 3 to the 18th is the same as 3 squared. This is working in U sub 5. And 3 squared in U sub 5 is 9 mod 5, which is 4. Another example. Let's take the cycle 25863 in the group of permutations S sub 8 and calculate this cycle raised to the power 593. Well, this is a cycle of length 5, and therefore its order is 5. As we saw earlier, a cycle of length 5 will be the identity, and no smaller positive power of that cycle will be the identity. So we calculate 593 mod 5. the cycle 25863 raised to the 593 is that cycle raised to the 593 mod 5, 593 mod 5. Doing things mod 5 is fairly easy, is a 3. And now we simply raise this cycle to the third power. We're going to do it, I'm going to do it like I've done previous problems. 2 is the smallest number appearing in this cycle, so I'm going to write the answer as a cycle or product of disjoint cycles starting with 2. So I'm applying this cycle 3 times to 2 in succession. The first application takes 2 to 5, the second takes 5 to 8, the third takes 8 to 6, 2 is sent to 6. Similarly, applying the cycle to 6 3 times in succession, 6 to 3, 3 to 2, 2 to 5, and so on. The point here is that we don't have to apply this cycle 593 times to each element. Okay, some properties of the order of an element. So if A has order n sub 0, then the powers of A starting with 0 and working up to n sub 0 minus 1 are all different, and every power of A is equal to one of these. This we saw earlier. If you take an a to the k, where k is any integer, a to the k will be the same as a raised to the power k mod n sub 0. And the remainder, when you divide k by n sub 0, has to be one of the numbers 0 through n sub 0 minus 1. And if a has infinite order, then for all integers m and k, if m and k are different, then a to the m will be different from a to the k. And now, if you have an element with finite order n sub 0 and some other integer k, under what circumstances will a to the k be the identity? This will happen if and only if k is a multiple of n sub 0. Or to say it another way, if and only if k mod n sub 0 is 0. So here's a definition we've seen before. Earlier in this set of slides, if A is an element of a group, then left angle bracket A right angle bracket is the subgroup of G generated by A, and it consists of all positive powers, all integer powers, not just positive, but all integer powers of A. And just to repeat some of the properties of this subgroup that we've seen before, if the order of A is n sub 0, then the subgroup generated by A has n sub 0 elements. And they are a to the 0 followed by the first n sub 0 minus 1 powers of A. And if A has infinite order, then you could write the cyclic subgroup generated by A like this, and 2 integer powers of A are different if the powers are different. A couple more examples. Let's find the subgroup generated by 7 in U13 times sub 13. So we know how to do this. We're going to calculate the positive powers of 7 until we get the identity in this group, which is a 1. 7 to the first is 7. 7 squared in U13 is 10. That would be 7 times 7 mod 13. 7 to the third is 5. I'll let you check my calculations. 7 to the fourth is 9. Still waiting for the identity here. 7 to the fifth is 11. 7 to the sixth is 12. 7 to the seventh is 6. 7 to the eighth is 3. 7 to the ninth is 8. 7 to the 10th is 4. 7 to the 11th is 2. Finally, 7 to the 12th is 1. So what is the cyclic subgroup generated by 7? It consists of the identity and the first 11 positive powers of 7. So what I've done to get the subgroup generated by 7 is simply copied the numbers in the boxes here between this set of braces. This 1 here on the end I didn't have to list, since I have 1 listed at the beginning. And this is all of U13. So it is possible for an element of a group to generate the entire group, as happens in this case. Okay, let's find the cyclic subgroup generated by 7 in this group, the positive real numbers using the operation of multiplication. 7 has infinite order. So what does the subgroup, cyclic subgroup generated by 7 look like? It's simply the powers of 7, the integer powers of 7. You can't do much to simplify this. I mean, you could possibly calculate the negative exponents, but not much simplification is possible in an example like this. So here is what's going to turn out to be a fairly important property of the subgroup generated by A. So let's suppose that you have a group G star, and capital H is any subgroup, not necessarily generated by an element, just a subgroup. And suppose little a is an element of G which is in H. Well, then the subgroup generated by A will be a subset of H. So this is a reminder here, which you probably didn't need, that the subgroup generated by A is the integer powers of A. So what we have to argue is, if we were going to argue for this fact, is that every integer power of A is in H. This is true because H being a subgroup has to be closed under the group operation and under taking inverses. Second property, the subgroup generated by the inverse of A is the same as the subgroup generated by A. The argument for this we would do by showing that each of these two sets, the subgroup generated by A inverse and the subgroup generated by A, is a subset of the other. So why is the subgroup generated by A inverse a subset of the subgroup generated by A? Well, an element of the subgroup generated by A inverse is an integer power of A inverse. And an integer power of A inverse is an integer power of A. And similarly, every integer power of A will be an integer power of A inverse. I'm leaving the fairly easy arguments for you to complete. Just kidding about the intermission, but if you've been listening to this video straight through, this would be a good time to take a break if you feel like you need one. Okay, and now we are going to talk about what's called a cyclic group. So a group G star is cyclic if there is some element A in G for which the cyclic subgroup generated by A is all of G. We've seen an example not too long ago where this happens. And if this happens, little a is called a generator of the group capital G. Or to be completely correct, a generator of the group G comma star. So let's try a couple of examples here. Is the group U sub 12 times sub 12 a cyclic group? Well, I don't have a quick way of doing this problem. I'm simply going to calculate the cyclic subgroup generated by each of the four elements of U sub 12 and see if any of those is all of U12. Actually, I can skip one. The cyclic subgroup generated by the identity will be just the identity. So we're going to find the cyclic subgroup generated by A for each A in U12 and see if any of those is all of U12. Well, the cyclic subgroup generated by 5 consists of the numbers 1 and 5. Since 5 squared is 1, using times sub 12. The cyclic subgroup generated by 7 consists of 1 and 7. It's also true that 7 squared is 1 if we use times sub 12. The cyclic subgroup generated by 11 consists of the numbers 1 and 11. The answer is no. U sub 12 times sub 12 is not cyclic. None of its elements generates the entire group. For no A in U sub 12 is U sub 12 equal to the subgroup generated by A. What about U sub 5 times sub 5? Well, here the answer is yes. I'm not going through the details of the calculation, but I did things the same way, and I found that if you find the subgroup generated by 2 in U sub 5 times sub 5, you get all of U5. And the subgroup generated by 3 is also all of U sub 5. You can check those two cyclic subgroups and make sure that I didn't make a mistake here. U5 is cyclic. And now what we could probably call the fundamental theorem of cyclic groups. A subgroup of a cyclic group is cyclic. So the rest of the video consists of proving this theorem. So we assume we have a cyclic group, G star, and since G star is cyclic, there is an element of G, we're calling it little a, for which the cyclic subgroup generated by little a is all of G. So we start with a cyclic group, and now we let H be a subgroup of G star, and our job is to show that this subgroup is cyclic. Which means we have to construct an element B in this subgroup for which the cyclic subgroup generated by B is all of H. This in general is how you would show that a group or a subgroup is cyclic. You find a generator. Well, if H consists of just the identity, then taking B equal to the identity will work. So we're going to assume that H has at least one non-identity element, which we will call C. And now remember that little a is the generator of the big group capital G. So we are going to compute powers of A, starting with A to the first, which is A, until we get an element of capital H. And this element will be the element B of capital H that will work. This will be the element of capital H that generates capital H. So in other words, we are letting B equal a to the n, where n is the smallest positive integer for which a to the n ends up in capital H. And now we have to argue that the subgroup generated by this little b is all of capital H. From a previous slide, a fact I mentioned on a previous slide, we know that since B is in the subgroup capital H, the subgroup generated by little b is a subset of capital H. So all we really have to show is that the subgroup capital H is a subset of the subgroup, the cyclic subgroup generated by little b. So we're going to take an x in capital H and try to show that that x is in the subgroup generated by little b. And how do you get into the subgroup generated by little b? You have to be a power of little b. So we're taking an x in capital H, and we are going to argue that x is b to the q for some integer q. Okay, so first of all, x is in H, so x is in G. Right? H is a subgroup of G, so H is a subset of G. So every element of H has to also be in G. Probably didn't have to mention this fairly easy fact. Since G is generated by the element little a, x has to be a to the k for some integer k. Right, every element of capital G has to be a power of little a, and for little x, we're calling that power k. And now we are going to divide k by n using the division algorithm. We've seen this fairly recently, this kind of thing. So if you divide k by n using the division algorithm, you get k equals some quotient times n plus r. The quotient and the remainder are integers, and the remainder is greater than or equal to 0 and smaller than n. Okay, so here's where we are in blue at the top. We know that b is a to the n, and this is the smallest positive power of a, which appears in H. And we've let x be a to the k, and we've divided k by n to get k is q times n plus r, where r, the remainder, is greater than or equal to 0 and less than n. And we're trying to show that x is b to the q. This is what we need to show that x is in capital H. Okay, so x is a to the k, and we know k can be written as q times n plus r, which we do. And then we use the rules for exponents. This is something we've done fairly recently on these slides. We get a to the n all raised to the q times a to the r. And then b is a to the n. So we replace the a to the n by b. So using the left-hand end and the right-hand end of this string of equations, we have x equal to b to the q times a to the r. We're trying to show that x is b to the q. We can do that if we can show that this little r is 0. Then x will be b to the q times a to the 0, or b to the q times the identity, or b to the q. So our goal now is to show that r equals 0. So I'm going to take this equation, x equals b to the q times a to the r, and multiply both sides by b to the minus q. On the left. So multiplying x by b to the minus q gives me b to the minus q x. And multiplying b to the q a to the r by b to the minus q gives me a to the r. B to the minus q times b to the q is b to the 0, which is the identity. Since b is in H and x is in H, b to any power of b will be in H. And when you multiply two things in H, you get something in H. So since H is a subgroup, b in H and x in H means that b to the minus q times x will be in H, which tells us that a to the r is in H. And remember, r is between 0, greater than or equal to 0, and less than n. N, remember, is the smallest positive integer for which a to the n is in H. So r can't be positive. R has to be 0, and the proof is completed. One final definition. We've shown that if you have an element of a group which has a finite order n, then the subgroup generated by that element, the subgroup contains n elements. So the number of elements in the cyclic subgroup generated by A is the same as the order of A. And now we're going to define the concept of order for any group. So if G is any finite group, the order of G is defined to be the number of elements in G. And this is usually denoted by G between absolute value signs.